Hello, everyone. Welcome to Open Hardware TV Season 2, Episode 4. Today's episode is about the projects that we have underway in our software task group. And as we've done with all of our previous episodes, we pre-record the content to try to improve the viewing experience. So all of our speakers are here online watching the video with you. It will be about 38 minutes. Take us to just past the bottom of the hour, 20 to the top of the next hour. And we'll have all the panelists will come back live at the end of the video stream, and we'll take your questions at that time. So over the course of the live stream, please enter your questions in the chat box. And sorry, not in the chat box, in the Q&A tab in the webinar tool here on Zoom. Enter your questions there, and we will take all those questions live after the end of the live streams. And so we'll see you back in about 38 minutes. Okay, hello everyone. Welcome to Season 2, Episode 4 of Open Hardware TV. In today's episode, we're going to cover all of the various projects that we have underway in our software task group. And the session will be led by Jeremy Bennett, the CEO at Embecosm, who is also the chair of the software task group. And we'll have project presentations from our FreeRTOS team, namely Robert Balas from ETH Zürich, and Shteryana Shopova from Embecosm. And then we'll also have presentation from the GCC and Lvm Tool Chain team. And that's Philipp Krones from Embecosm and Jessica Mills as well from Embecosm. And we'll all then have a presentation on the IDE environments that we're working on, both at Eclipse and PlatformIO. And we'll have Ivan Kravets from PlatformIO Labs and Alexander Fedorov from Arsysop and Eclipse. But before we get into the episode, just want to give you a quick overview of the Open Hardware Group and what we're working on with the CORE-V cores. So the Open Hardware Group is an international nonprofit organization registered in Canada that focuses on the development of open source hardware and software specifically related to clustering processor cores, and namely the CORE-V family of open source cores that are RISC-V based. We have an international footprint with developers in North America, Europe, and Asia, many supporters around the world. And what we're really providing is an infrastructure for the development and collaborative development of these open source artifacts. We have strong support across the industry, both from commercial companies, research institutions, and individual contributors. We have a very strong ecosystem on the industry side with 64 plus members and partners. And the commercial companies are large organizations, smaller companies, semiconductor companies, systems companies, tool chain companies, hardware developers, and software developers throughout these organizations. We also have a large research ecosystem in the Open Hardware Group with many world-leading institutions that are doing research using our open source cores, as well as a strong partner ecosystem that help us curate these open source artifacts and deliver them into the ecosystem. The way that we're structured is through a series of working groups, namely a technical working group and a marketing working group. And under the technical working group, we have several task groups. The cores task group, which looks after the CORE-V cores themselves, the verification task group that does the verification work associated with the cores, the hardware task group that implements these cores into FPGA implementations as well as SoC implementations, and then of course the software task group, which you'll hear more about today. And the software task group is chaired by Jeremy Bennett, who you'll meet shortly, from Embecosm, and the vice chair is Yunhai Shang from Alibaba. And that team is chartered with developing and supporting the software tool chain, operating systems, firmware, IDEs, basically the whole software enablement environment in support of the cores. So with that, I will hand this over to Jeremy, who will lead the rest of the session and introduce the various projects. Jeremy, welcome to Open Hardware TV.
Thank you, Rick. Welcome to today's episode, where we're looking at the work of the OpenHW Software Task Group. And we're going to address 3 of today's projects. The first project we'll be looking at is our work with compiler toolchains. And we'll hear from Jessica Mills and Philipp Krones about the development of GCC and Llvm compilers for the CORE-V architecture. The second talk from Shteryana Shopova and Robert Balas will look at their work bringing up the FreeRTOS operating system for CORE-V and getting it working on our reference FPGA and SoC platforms. And our final talk will be Ivan Kravets and Alexander Fedorov looking at IDEs within which you can develop all your software. And we'll be looking at Eclipse CDT and PlatformIO and how the 2 of them can work together so you get the best of both worlds. These aren't our only projects. We have others in progress. In particular, we have quite a lot of work going on providing software models for the software engineering team so you can develop your software before your silicon chip's ready. We have OVP Sim from Imperius to provide you with high-speed models, and we have, for those who need more accurate models, we are developing Verilator models for cycle-accurate modeling of the chips at the low level. And you'll hear those referenced later on during the talks we have in progress. But we are a living project, and I want to just say a little bit about where we're looking to in the future. The first thing is we need to generalize our work so it works on all the CORE-V family now and in the future. So that means things like the CV32E40X, the generic chip with generic instruction set extension interface, the CV32E40S, the security version of the chip aimed at security applications, and the application class core, the CVA6, in its 32-bit and 64-bit versions. We need to support all of those. And we need to recognize that while FreeRTOS is a very widely used and popular real-time operating system, there are others that people use. For example, Zephyr is very popular as a real-time operating system for RISC-V applications, so we'd hope to bring Zephyr up fairly soon. And for application class processors like the CVA6, we're going to need full fat operating systems as well. The obvious one being Linux, but there are operating systems like FreeBSD, which are particularly popular within security applications. And the final project, and one which we are getting going in the very near future, is a definition of a hardware abstraction layer. We aren't going to be able to rewrite all the code every time a new chip comes along or a new operating system comes along. And that's the purpose of a hardware abstraction layer. And we'll be developing our own hardware abstraction layer, but we will very much be looking at how do we do that, making best use of existing practice within the RISC-V community. We're not aiming to invent something completely new for ourselves. So that's what we're looking forward to in the future, and we hope to come back to you with a future episode where we talk more about these. But for now, let's go back to our existing projects, and I'll hand over to Jessica Mills and Philipp Krones to tell you about the GCC and Llvm for CORE-V projects.
Thank you, Jeremy. So we've been working on extending the RISC-V, GNU and Lvm tool chains to support the CORE-V instruction sets shown here. To make it clear that the tool chain is targeting CORE-V, we use the vendor field of the target triplet. Thus we have RISC-V 32 CORE-V ELF instead of RISC-V 32 unknown ELF. Additional architecture specifications can be used to specify either the whole CORE-V support or just selected parts. For example, an march option of XCORE-V will enable all CORE-V instruction extensions. However, an march option of XCORE-V Mac will only enable multiply accumulate instructions. All CORE-V instructions have a CV prefix. The toolchain has built-ins for the majority of instructions. As well as built-ins, the toolchains are able to recognize patterns and optimize to use CORE-V instructions. For example, on the slide here, we have the map function that computes the product of two numbers, A and B, and adds that to an accumulator, res. There is an option to use the CORE-V built-in or simply write the equation where the pattern will be identified and optimized, resulting in a reduction in code size as seen on the right. So a brief introduction to the GNU toolchain. Here we have all the components which make up the modern GNU toolchain. For a standard RISC-V, we can already compile Ada, C and C++, and in future, Fortran and OpenMP. We have the compiler GCC, the GNU assembler GAS, and the GNU debugger GDB, and a set of binary utilities. We have low-level libraries to support C and C++ on any RISC-V variant, and a range of standard C libraries for systems both large and small. Our initial focus is to extend the compiler and assembler, highlighted here in red, to support the CORE-V instruction set extensions. So I'll now hand over to Philipp, who will give a brief introduction to the Llvm compiler and demonstrate both the CORE-V GNU and Llvm compilers side by side, showing their similarities.
Thanks, Jessica. We now take a look at a simplified view of the Llvm toolchain. So the Llvm toolchain consists of three parts. The first part is the front end, where we define things like built-ins, like we saw before. The front end can be one of many for different languages, like the Clang front end for C and C++, the Rust front end for the Rust language, or for other languages. Currently, we're only working on the Clang front end for the CORE-V toolchain. The second part of the Llvm toolchain is the optimizer. Here we implement things like the hardware loop optimization, where we can turn a mem copy into a hardware loop, so it has increased performance on the target. And the last part of the toolchain is the backend, where we then turn the optimized code into code the target can understand. This can be a classic backend like x86 backend, or like in this case, the CORE-V backend, where we then produce instructions for the CORE-V target, like the CORE-V make instruction we see below. And now we show a short demonstration of what both toolchains can do. As the first demonstration, we will look at a mem copy. So we have a struct S, which has an array B, and we then copy one instance of the struct S to another instance of the struct S with this instruction A is B. If we do this with just the RISC-V toolchain without any extensions, we will see that in the end, we will get just a loop. So the loop, you can see the loop here, which will just loop around and copy one element after another to the new address in memory. But if we change the previous command and enable the hardware loop extension with Mco hardware loop, HWLP. So we get a little bit different output here. We have now a CORE-V setup instruction, which will set up the hardware loop, which is optimized code in comparison to just a normal loop we will get without the extension. And it will then execute a loop directly on the hardware instead of instruction after instruction, as we would get in the first instance. The second example we will look at is the multiply accumulate example we saw before. We have three arguments. We use the first argument as our accumulator, then we multiply the source 1 with source 2 and add a product to our accumulator, and then we return our accumulator. If we now compile this again with the CORE-V Mac extension enabled, we will get So if we look at the output, we see that the CORE-V Mac instruction was used instead of executing the multiplication first and then the addition. It is all in one command. So we save a little bit of code size. If we look at the same example, so the implicit copy with the Lvm tool chain, we see that we kind of get the same output. We also have the hardware loop here. And it's a little bit more code. This is because of a bug in the Lvm tool chain we still have right now, which we're working on fixing, where we can't optimize this code. So, but we still see that also the Lvm tool chain is able to produce this hardware loop code for an implicit mem copy. And the second example, the multiply accumulate example. If we compile this with Clang, we will see that we get the exact output as with the GCC toolchain, where we have one instruction, CORE-V Mac, which multiplies and accumulates in one step instead of two. So if you want to get involved with the Lvm toolchain development, you can join the OpenHW Group MetaMost channel, or specifically the Lvm Tools channel. Or you can also join the OpenHW Software Group mailing list. Or if you just want to get your hands on the code, you can also just check out the OpenHW Group CORE-V Lvm project on GitHub and start hacking on the code. That's it from me. And now I will hand over to Jessica.
Thank you, Philipp. So if you wish to try using the new CORE-V GNU compiler, you can download a convenient pre-built binary from the Embecosm website. You'll find versions for all the major operating systems, along with links to the source code, scripts to build the toolchain, and test results. But we'd also encourage you to become developers. You can find out more via the OpenHW Group MetaMost Software GNU Tools channel. As Philipp mentioned, you can sign up to the OpenHW software mailing list and attend our monthly meetings. And finally, we'd welcome your pull requests against the development codebases on GitHub. Thank you for listening, and back to you, Jeremy.
Thank you, Jessica and Philipp. Great demo of the compiler work that's in progress there. Our next talk is from Shteryana Shopova and Robert Balas, who are going to introduce us to the work they've been doing on FreeRTOS. Over to you, Robert and Shteryana.
Thank you, Jeremy. So what is FreeRTOS? FreeRTOS is a real-time operating system for microcontrollers. It consists of a real-time kernel plus a set of optional libraries. A lot of architectures are already supported on FreeRTOS, among them RISC-V. You can think of FreeRTOS as a thread library that is linked with your program rather than a classical full-fledged OS. But there are also a set of POSIX-like IO add-ons and also a command line interface. Development of FreeRTOS happens in the open on GitHub, and Amazon is upstream since about 2017. So why FreeRTOS? FreeRTOS enjoys a broad industry adoption. It calls itself the market-leading real-time operating system. It supports more than 40 different architectures. There is professional support available, and there are also multiple supported IDEs and tool chains you can choose from. There are various libraries that address your IoT needs, such as generic IoT libraries, MQTT libraries, HTTP, TCP, POSIX-like IO extensions, and a command line interface. Finally, FreeRTOS is liberally licensed. The kernel is MIT licensed, and our contribution from the OpenHW Group are Apache licensed. So how do FreeRTOS and the CORE-V MCO fit together? So first of all, we want to demonstrate the capabilities of the CV32E40P on FreeRTOS. Furthermore, FreeRTOS allows users to develop applications for the CORE-V MCU. And finally, it is useful for the verification team to do system-level testing. So what is the current status of FreeRTOS on the CORE-V MCU? Currently, we have running Blinky, the UART driver, and the kernel ported to the CORE-V MCU. Our repository packages the kernel with a UART driver and a few examples. More features are in the planning and upcoming, and you can check out the CORE-V FreeRTOS version on this GitHub link. Thanks for listening, and I'll hand it over to my colleague Shteryana right now.
Thank you, Robert. So what this slide is really about is some of the issues we encountered while porting FreeRTOS on the CORE-V MCU. We hit some bugs. The most serious issue was hang during FL access, which is now fixed. We've hit some RISC-V ISA compatibility issues, which have been fixed or are still being fixed. Some of the work we reused from the Polpissimo FreeRTOS, and there's still some work that needs to be done, like some hardware changes are in progress and they will eventually require software adjustments. And now I'm going to play a little demo for you. I'm going to start the video and explain what I'm doing in the video. And this is actually demonstrating the Blinky application on a Nexus A7-100 FPGA board. Okay, so this is me actually flashing a bitstream to the Nexus A7 FPGA board, connecting to the target. Now selecting the proper bitstream file. Once this is done, I'm exiting Vivado Lab since it shares common ports with OpenOCD. So this is running Minicom to see what's going on the UART. Now launching Eclipse and configuration for uploading the software on the FPGA board and starting GDB, the OpenOCD. So at the bottom of the window, we can see some stuff is going on. So the build finishes. It takes a while. So OpenOCD has successfully attached to the board, and the remote debug connection is launched. And here the execution stops at the program entry point, the main function. Next, I'm setting a breakpoint at the main Blinky function, so the execution will stop once we reach it. Now continuing execution. Some demo of stepping into the function. And then once execution is resumed on the UART, we can see the application actually printing on the UART. So that was the end of the demo. Hopefully we have some more cool stuff coming soon. And back to you, Jeremy.
Thank you, Robert and Shteryana, for that demonstration of your progress with the FreeRTOS project. Our final talk today is Ivan Kravets and Alexander Fedorov telling us about the work they've been doing to develop IDEs for CORE-V. So without further ado, over to you, Ivan and Alexander.
Thanks, Jeremy. At the PlatformIO Labs, We believe that the embedded system industry desperately needs reinvention. Not only the ideas and tools built with technology from 19 years, but the complex requirements and platform-dependent configuration actually turn away talented developers from becoming embedded engineers. At the PlatformIO Labs, we provide the next generation technology for semiconductor industry, hardware manufacturers, cloud software providers, IDE providers, and academics. Both of them share the same need. They need the free, full-featured professional development environment. Our company provides complete solution for their needs. But what is the reason why we joined to the OpenHW Group? There are a few of them. The first, we want to provide a free, neutral, and independent collaborative platform for developers and teams without being locked to the particular vendor. It will give developers full freedom and allows them to work on hybrid configuration-based project and use their favorite code editors or operating system. The second reason, we provide software and hardware agnostic platform where companies can integrate their solution to the PlatformIO ecosystem and developers can benefit from this. It can be advanced debuggers, static analysis tools, simulation tools, or advanced integration services. And the third reason is to help semiconductor industry to speed up time to market when launching CORE-V based products in weeks instead of months or years. The interesting question is, how do we benefit from the OpenHW Group? And the answer is very simple. Being a member of OpenHW Group allows us to be at the edge of software and hardware worlds. Thanks to the OpenHW Group, we can work with the professional in the semiconductor industry. We can listen to them and increase adoption of our technology. Also, we can help customers who plan to use CORE-V based for their future products to save on developing yet another IDE. Because thanks to our technology, they can reuse our next generation framework and modern UI toolkit to build the next generation IDE for decades, but not for the years. And what is actually the PlatformIO? The PlatformIO is the vibrant community with our 2 million developers around the world. We make them happy because we don't require them to be high-skilled electronic engineer. Having a great idea is very easy with PlatformIO to implement it because no need to know anything about the real hardware. PlatformIO solves these issues in the background. Now, I would like to demonstrate what we did for the OpenHW Group and show you a real demo how to work with the project based on CORE-V core. In this example, I will use Microsoft Visual Studio Code and official PlatformIO extension. You could do the same from your side. Just download official Microsoft Visual Studio Code editor, go to the extension tab, search for PlatformIO IDE, and install it. I already installed that. Now just press the home button. Now you just navigate to the project examples and search for OpenHW Group examples. And you will see a few pre-configured examples, and I will start from the first using Pulp SDK runtime sort. Just press import, and PlatformIO will open project for you, pre-configure all tool chains, and you can open the main source file. So, and now we can try to build the project, which is very easy. Just press to build. But the main goal of this demonstration is to show you the real debugging process. As I don't have the hardware, we will use the simulation tool. In this case, we back again to the PlatformIO home. Go to the project configuration and type debug tool. debug tool and set it to Renault, because you can use it on any operating system. If you prefer to use OVP simulation tool, you can type OVP sim in this sim, but it doesn't work on the Mac. I will use Renault. Just press save, finish. Now go to debugging tab and start the debugging process. The project is compiled in debugging mode, and now we see debug console that Renault is started. We should wait a few minutes when debugging server will dig to the front end, and we should stop at the main function. We can go, we can step our code. Now let me try to clean the debug console, because the next line is the print line. You see, like getting started example. You can go next. You see the getting started example. You can go to any line, like run the cursor, and we see somehow. So this is the quick demo. We see that no need to be any electronic engineer, no need to be expert in the embedded development. If you are a talented C++ engineer, it's very easy to get started with CORE-V products, because the rest we already done. So now I want to ask Alexander to show amazing demo of how he integrated CORE-V into the Eclipse solution.
Thank you, Ivan, for introducing my presentation. I will start from giving more context what the CORE-V IDE is and how we do that. So the CORE-V IDE effort is fully open source, and this is important. We have our own repository and also under OpenHW Group, and all the work is done under the Eclipse public license. So you're really welcome to join. You can just fork that repository, clone the sources. There are build instructions how to do all the stuff. You just need Java and Apache and internet access, and here you go. So technically, the CORE-V Eclipse-based IDE is an aggregator of a lot of components from Eclipse ecosystem. Here I demonstrate you the sources of the CORE-V IDE, how it's represented inside the IDE, and you can see that it has a lot of well-known components embedded to it. So it has Eclipse platform, it has CDT and embedded CDT and a lot of others. And now we also managed to bring the PlatformIO stuff in. It's actually not easy because PlatformIO has another technology stack. They're fully JS based, but with our expertise it is possible. So I would like to show you how it looks like. Let me run it. So the magic is here. The PlatformIO client that was already presented by Ivan can be seen on the Eclipse environment, and we built simple integration to just demonstrate that it is possible to use that simultaneously. Okay, let's try to select the board. It will be, I think, A7, not Cyrillic, not English. And using POP SDK, and the project name would be i7, I think. So we are creating the project, and that project is automatically imported to the Eclipse IDE. Now we have a project that is configured to run with internal Eclipse facilities, not actually internal, with CDT, C and C++ development tools, and also other functionality also works. So we can try to run inspect, for example. I will use, I think, the project, another project, just to keep it faster. So I will show you with an example of UNO project. I just need to open it. And you can see it is here. And then while it's opened, I can run the inspection. I'm opening it actually to have a target to navigate to the sources, because PlatformIO will report me some defects and I would like to see them in the source code. So you see that the navigation selects the corresponding line. Actually, here's a challenge start, because Eclipse is much more rich platform than VS Code, and typically Eclipse uses problem view with much more precise information regarding problems in the code up to symbol range and so on. And also, yes, I can see it's a bit, yes, probably, yes, it's insufficient for that. But this is the very basic stuff. So the plan is to improve that. And actually, we can also have more deeper integration with the debugger facilities. We do support a lot of debug capabilities already through component that we have inside. Again, it's the CDT, embedded CDT, and classic Eclipse platform with modeling project. And we allow to create the project in the, let's say, regular way through C, C++ project building. But this is not so deeply developed currently, because the toolchain production for CORE-V is still in progress. But we are looking forward to get more templates and more examples from our colleagues from the software group to improve that scenarios. The same for debuggers. How can I do that? Yeah, probably from classic C and plus or debug perspective. Yes, just to show what is already here. So yes, we expect to integrate even more debug capabilities. Especially, we are interested to integrate the hardware-less, let's say, capabilities like Renault, to have an ability to test without real hardware. And again, all this effort, the PlatformIO Eclipse integration is also open source. It's available under Apache license, and you're also welcome to contribute to it and use it. All your issues reported and pull request or any other contribution like documentation, test cases, whatever, is always welcome for PlatformIO work and for CORE-V ID work as well. Thank you for watching the demo. Giving it back to you, Jeremy.
Thank you, Ivan and Alexander. Great to see the work you've been doing on the IDEs and how you've managed to get Eclipse and PlatformIO to work together so effectively. That's the last of our talks today. I hope you've enjoyed them. My thanks to our three groups of speakers, Jessica and Philipp on the compiler projects, Shteryana and Robert on the FreeRTOS development, and Ivan and Alexander on the work on IDEs. Now back to you, Rick.
All right. Thank you very much, Jeremy, and to all the project teams. We're now going to open up the session to live Q&A with the attendees. All right, welcome back, everyone. Sorry for the little glitch we had right at the outset. I'll ask all the speakers to unmute their mics and turn their cameras back on so that we can take the questions from the attendees. And just while we're getting started on that, we had a generic question just around the video recording and so on. All of the OpenHW TV webinar sessions are recorded, and you can watch on demand at any time. Just go to openhwgroup.org, and on the OpenHW TV drop-down menu, it'll take you to the page where there's links to all the videos from all the episodes in season 1 and the new episodes here in season 2. So you can go and navigate to those. I have a few generic questions that we'll sort of throw out there. One is related to available hardware. Where can we buy available hardware to use? Is it available now or soon? And then a question related to hardware vendors and how they can play with Eclipse and PlatformIO from a learning standpoint. So I'll take the available hardware one. And I'll let the rest of the speakers comment on this too, as they've been playing with the hardware. But the OpenHW Group has several task groups, as I presented in the intro. But a parallel task group to the software task group is a hardware task group that's responsible for both FPGA and full SoC implementations that use the CORE-V family of cores. And in particular, the demos, the demo that Shteryana showed, and the work that the IDE team are doing, as well as the compiler work, are targeting an initial bring up of a device called the CORE-V MCU, which uses the 32-bit RISC-V core that we have in the CORE-V family, the CVE4. And that's available now in an FPGA platform, both Nexus A7 boards and Genesis 2 boards, as well as will be available in a SoC that we're going to build with Global Foundries and 22FDX on an eval board. And that project is being driven by the hardware task group. We don't have availability of the board yet or pricing. The actual configuration of the board and features and functionality that will be on the board is being specified now by the hardware task group. So if you'd like to influence that, you're more than welcome to participate in that group and drive some of that. But I know that each of you, from a panelist standpoint, so I'm going to sort of throw it over to you guys and ladies to comment on. You've all had probably a different varying amount of experience of either using software simulators to bring up your tools, or the FPGA environment that we have to bring up your tools. And much of it has been a work in progress. But if you guys can comment on your experience with the hardware so far, that'd be appreciated. Jeremy, why don't you start, because I know you've done some playing too.
Yes, so I think it's a very good question, Rick, and it actually speaks to one of the projects we didn't present today, which is why we have these tasks looking at modeling. And that is important for a number of use cases. And in fact, one of the issues for the compiler team is when you test GCC, you have something like 100,000 C tests to run 150,000 C++ tests. And that's hard to do on small boards. It can be done. So we typically do the nightly testing using simulators, and that's where OVP Sim and the Verilator model come in. I think the team with the biggest experience here is Shteryana and Robert, and Shteryana can perhaps say a little bit about her experience of using the actual hardware. And then Alexander might like to say just a little bit about how he's trying to set up the Eclipse world so that if you don't have hardware, you can use a simulator and it's pretty seamless. But Shteryana, you might like to share a little on your experience of actually using the hardware.
First I want to say that I think using simulators and running on actual the hardware are complementary approaches. I think both should be done simultaneously. Since I still don't have access to simulators for the CORE-V MCU platform, I've been using an FPGA board. Things happen slower there. And I totally agree with Jeremy that actual hardware might not be practical for things like nightly tests, etc. But on the other hand, running the software on an actual FPGA board might reveal some problems that would otherwise not be seen on running the software in simulation. So it's slightly slower. Sometimes Depending on the setup, you might need to do repeating things, tasks like flashing bit streams, waiting for debuggers to attach, etc. But that's just the way embedded software is being developed.
Thank you, Shteryana. And I think one of the important things is that because we're developing the software while the hardware is still being developed, I mean, Shteryana and Robert have fed back useful information about the design of the hardware board to make it more suitable for software. It's always the best way to do things. And I know the implementation of the timers, I believe, has been modified to make them more suitable for operating systems. Alexander, you had a particular issue that you couldn't immediately get hold of hardware. So for you, it was a practical need. And I know you've been working with Imperius to put OVP sim in the IDE. Would you like to say a little bit about that?
Yes, that's true, because it could be a location-based restriction, as you know, in the modern world. And it is important to have an ability to test your software without real hardware. I believe that a lot of testing could be completed without hardware available. But yes, Shteryana is right. Some of the tests could be done only with real hardware. But we all know that there is a hierarchy of tests from lower level to higher level. So I believe that ability to test without hardware just speed up the development cycle. As for our connection with Imperius, thanks to them, they contacted me. We started to talk, and we are in connection to provide some solution for the CORE-V. I don't believe it will be a part of distribution, of official distribution, because the Imperius solution is not open source, but we will think how to make it freely available and installable together with Imperius. Back to you, Jeremy.
Okay. So I hope that gives you a feel for where we are with the hardware, but I think the takeaway is that now's a really exciting time to be involved with the software, because things you find out doing low-level software will influence the hardware design. Yeah,
exactly. Just a reminder to the attendees, if you have questions for this group, feel free to put them in the Q&A tab. You've got some experts, embedded software development experts here, deeply involved with open source RISC-V implementations. So make sure to ask a question of them. There was interest in PlatformIO, how to start using PlatformIO and creating, and a vendor our hardware vendor, creating their own examples for loading and use within PlatformIO. So Ivan, are you able to give some guidance on that question? So specifically, it's about if a hardware vendor wanted to add a new example into PlatformIO, how would they do that? I think you're on mute, Ivan.
Sorry, thanks, Rick, for the question. I have just a few comments to the previous questions related to the hardware. So the PlatformIO, we actually split it between two teams because, one team works on the integration with frameworks and simulation tools. In this case, we use real hardware. And there is the team who works with IDEs and user interfaces. In this case, we use simulator tools. And the great benefit of the PlatformIO is that you can simultaneously use multiple different simulation tools. Because some of them support a particular operating system and other doesn't support. So you can be flexible depending on your host machine. If you are on the Mac, you can use one simulation tool, or when you're on the Windows, you can use another. And now let's back to the main question related to how to provide custom integration to the PlatformIO. It's very easy. So the first, the development platform, which is actually the plugin to the PlatformIO, which connects OpenHW Group products into the PlatformIO ecosystem, is open source. and we plan to move this repository to the OpenHW Group. So everyone will be able to go down through the source code and understand it's very easy. So the first, from the end side, you just need to provide and explain PlatformIO how to do build process, how to do debugging, unit testing. And after that, you receive full-featured development environment with debugging, unit testing, firmware inspection, and no need to worry with code editor or operating system. Back to you, Rick.
All right. Thank you, Ivan. I have another question. It's kind of generic, and from the software community, be interested to get you guys your take on this. It related to, and I used to get this all the time when I was running the RISC-V Foundation. Will RISC-V ever challenge ARM or x86? So I'll give my answer, and then each of you can offer your opinion from the software standpoint. And as I said, I used to get this question all the time when I was running the RISC-V Foundation, and it's really not about, it's not an exclusive OR function. This is not, RISC-V is not an architecture that is going to stop ARM from existing this week, this month, this year, this decade. Or x86. Clearly, both of those architectures have been very, very important to the technology sector and the growth of both server class environments and handheld and applications and so on, smartphones as an example. Where RISC-V really helps is the ability to tailor a purpose-built architecture, a purpose-built device that is very, very power efficient and performance efficient to address a particular application need. The fact that it's an extensible ISA, meaning that there are standard extensions that you glue together, if you will, and only the ones you need to use in your application are what you include in the hardware, and has the ability to include user-defined extensions and instructions, as we demonstrated with the hardware loop instructions that were developed at by the Pulp team at ETH Zürich, and the customization for LLVM and GCC tool chains to take advantage of those hardware instructions. You can achieve very, very good code density, power efficiency in the overall implementation, and it's not instead of the ARM and x86 architectures, but it's as well as, right? We're going to see increased heterogeneous compute clusters that leverage different architectures, either because of code base, historical adoption, and then new efficiencies that you can implement using RISC-V. So I don't ever see it as like I said, as an exclusive OR. It's an AND function. It's not an OR function. And the computing need for greater performance at lower and lower power footprint is where RISC-V is going to continue to help. Software panel, we're just about at the top of the hour, but I'll let you guys, any of you who want to take an approach to that question, go ahead with anything further you want to add to that.
So I think
Jeremy, I'll let you start.
Yeah, so this is very appropriate for a software task group, because I think a lot of people forget that ARM's great breakthrough when they launched was not just their chip, it was the real view debugger and the idea that you shipped an embedded device with a really powerful software tool chain. So as far as ARM, I suspect historians will look back and say, actually, RISC-V was good for ARM because ARM had become so monopolistic. Actually, you've seen ARM's policies change. They've got much more flexible about configurability. The big advantage of RISC-V is configurability. I think the big risk for RISC-V is matching ARM's software ecosystem. And that's where I think the OpenHW Group's taking a leading role. If you see the focus on software, the focus actually on delivering software, not talking about standards or what software ought to look like, but just getting it done. So you see great progress over the last 8 months on both GNU and LLVM tool chains. We've got the most popular free real-time operating system up and running. We've got 2 IDEs up and running, and that's going to be the differentiator. There's far more software engineers using the chips than the actual chips. So that would be my take on the ARM, and ultimately it's good for both of us. ARM will thrive, so will RISC-V.
Anybody else want to chime in? There's one more question I'd like to throw out. I know we're over time, but I'll toss this one out there because it was specific to some of the material that was presented. Why did we show PlatformIO integration with Eclipse CDT as opposed to Eclipse Thea, which is obviously Visual Studio Code based? So Ivan, and Alexander, maybe if you guys can each comment on that.
Yes, so the quick answer, we will have soon support in the Eclipse Thea. There are just one limitation. There is no extension for C++ development for the Thea. In case with the Visual Studio Code, we moved away from Microsoft C++ extension because it isn't open source, and so the problem with the license. And we are on the way of moving from this C++ extension, so it will be announced soon, the support for Eclipse Thea. The same for the VS Code is very similar code editor to the Visual Studio Code, but without Microsoft limitations.
Got it. Thank you. All right. Well, we're past the top of the hour, and thanks for staying with us, attendees. And I'm sorry again for the small little hiccup that we had at the very beginning. This is the end of the episode. It will be captured, it is being captured, and will be available for download on the Open Hardware TV tab on openhardwaregroup.org. So thank you to all of our software task group project leaders and speakers. And wherever your day is, I hope it's a good one. Thanks for joining us.